Hi, everyone. Today we're going to be going through chapter A3.4, which is the applied chapter for forest degradation and deforestation. My name is Crystal Wespestad. I work at a spatial informatics group, and I was a collaborating author for this chapter along with Carlos Souza Jr., Karis Tennyson, John Dilger, and Eric Bullock. So we'll go through the overview of this chapter, the theory behind change detection for forest degradation and deforestation, and the practicum with the scripts in the book. So what is our goal? We're going to use spectral unmixing algorithm and the normalized difference fraction index, or NDFI, to detect and map both forest degradation and deforestation. We'll go through two different examples, one comparing a pair of images using an empirically defined change threshold, and then applying a more extensive and dense time series approach called coded. So by the end of this chapter, you should be able to calculate NDFI, interpret fraction images and NDFI using a temporal color composite, analyze deforestation and forest degradation with NDFI, and run a time series change detection and detect forest change. Namely, we'll be focusing on coded. And it expects you to know some basics from previous chapters. So, some basics about forest disturbance. Disturbance is the broader term that encapsulates both deforestation and degradation. Deforestation is the complete removal of trees where a land use or land cover change has completely switched from forest to non-forest, such as agriculture. Whereas forest degradation is a more temporary disturbance, or it can be permanent, but it's not a complete loss of the trees in that case. There actually is no official definition of degradation that is accepted by everyone around the world, so it's hard to define, but we'll stick with where the tree loss does not entirely change the land cover type. So it either is partially lost or it's fully lost temporarily and then recovers. Both can be smaller scale and shorter in time. So the buzzwords for what is degradation, it's ephemeral, meaning it can disappear very quickly. So it can only be seen with a few Landsat images often. It can be subtle. So it could be a partial canopy cover or in isolated areas. So just a partial loss. And it can have small scale impacts. Sometimes, especially for selective logging, it's just in little lines through the landscape. So it is often at the sub-pixel scale of the 30-meter Landsat imagery, which makes it hard to analyze. So all those things make it difficult. And the solution that we're applying here is called spectral mixture analysis, or SMA. So this method has been proposed to overcome these challenges where not the whole pixel is affected. It's based on the linear spectral unmixing model. Landsat pixels typically contain a mixture of many components. You'll often see this when you're trying to do analysis, where half of it is one land cover and the other is another land cover type. So this method identifies the nature and number of pure spectra, which we'll call N members of the land cover components within the image scene itself. So those N members are what's in this image here, abbreviated as GV for green vegetation, soil, non-photosynthetic vegetation, and shade. So we can combine all of those N members in an equation that gets us what we call the NDFI. So I've been using the term NDFI, normalized difference fraction index, thus far, but you're probably more familiar with NDVI, which is the normalized difference vegetation index. And that's just the ratio of near infrared minus red over near infrared plus red, which has traditionally been used to identify healthy vegetation or the presence of vegetation. NDFI works in a very similar way, except it's believed to be more sensitive to small scale changes in the vegetation health and cover. So if it's an intact forest, it should have a very high NDFI and NDVI due to the high GV shade in the ratio and the low non-photosynthetic uh, NPV and soil values. So most of the pixel would be GV shade, which is a combination of GV, the green vegetation divided by 100 minus shade, compared to the amount that is non-healthy photosynthetic vegetation and bare ground soil. Degraded forest would be a mixture of the two. So the NDFI is comparatively lower than the original healthy forest value. And then deforested areas would have a low NDFI due to a very low GV and a high proportion of shade and NPV and soil. Sorry, low GV and shade and high NPV and soil. So this is a time series showing a healthy forest that has high NDFI values. An event occurs where something has happened to the forest, it's degraded, and you can see a partial drop and then eventual recovery back to normal values. And then another event happened where it dropped significantly, and then the spectral signature changed into a different harmonic here. So if you look at what is actually happening in the images, in 1991, there is a small scale disturbance, maybe a partial cut. By 2020 or 2002, it has recovered to forest, and it's you can see that in the optical imagery, and it's green in the NDFI map. But then you go to 2008, and there has been a larger scale full cut of the forest where all the trees were removed. It shows a bright red for very low NDFI. So NDFI, in summary, is especially good at detecting degradation. It also can detect deforestation. It's just a more severe change compared to the other spectral indices, namely NDVI. So this is just one good example of both of those changes in sequence. So let's look at the practicum now, which is where we will go to the repository for the book. You click on that link. I actually have it open in another tab here. We're going to the A3.4 Forest Degradation and Deforestation chapter. There are several checkpoint scripts. There's also a module with a palettes script, which is just some referenced code for this very large color ramp that will be used in the visualization. You don't need to mess with this one at all. It's just referenced. And then there is a local version of the coded repository or the script for coded, which we'll get to later. Let's start with the first part of the chapter, so this is showing the ratio or all those different N members that are in the ratio for NDFI. Again, we'll define the Landsat N members, create a function to use the N members and create the NDFI image, add the SMA bands and the NDFI bands to the map, and apply a cloud and water mask to the NDFI band using update mask function. Then eventually we will use that process to compare two images. So we'll observe the changes over time by creating an NDFI image for two different points in time and showing the difference, applying an empirically defined threshold to classify the changes based on the inspection of the histogram. So let's go to the checkpoint A34A. Right here. And you can go from the book, be copy pasting. Okay, so if you are in the book chapter, you can go to the gray boxes of code and copy paste these one by one into your script. So if I jump ahead to the checkpoint 1, which already has all of those copied, that is going to be the listing of the N members, so the spectral values for green vegetation, non-photosynthetic soil, and cloud. These vary across landscapes, but these are some accepted values that will generally work. We'll also be importing a single Landsat image and centering the map on that image object. And we will be defining the bands using Landsat 8 specifically that we will want to select. And then using an unmixing image using singular value decomposition with a function. So if I go back to our script, this is the first checkpoint, which already has the script copied. The N members are defined. We'll select a Landsat 5 single scene, and that will center our visualization of the map on that image. We're only going to select certain bands from Landsat 8. If you want to switch to Landsat 5, those band names change very slightly so that we can have the red, green, blue, etc. And then we'll use an unmixing image singular value decomposition. So this function gets the SMA fraction by selecting visible bands, near infrared, and shortwave infrared bands. Those are these. You unmix those N members and rename them to something that's more human readable, and it will return an unmixed image. Then you can calculate the GV, which is the green vegetation, and NDFI, and add them to image fractions. So you're running the SMA model by passing the Landsat image and the N members into that function. So our single Landsat image, and then our N members of the spectral values for what does shade look like, what does non-photosynthetic vegetation look like, etc. And we will add that to the map. So this is just the fraction of SMA with bands of NPV, GV, and soil for the red, green, blue. Then it will calculate the shade and green vegetation, shade normalized GV fraction from the SMA bands. So it'll make specifically a shade variable, a GV variable, selecting just GV, and add the new bands to the SMA image variable. So SMA.add bands, specifically shade and GV. Now that we have all of those, we can actually calculate the NDFI. So you can see the equation, which we referenced in the chapter. It's a function of GV minus NPV plus soil over GV plus NPV plus soil. So it's selecting each of those bands from the SMA image. And then we'll add the NDFI, actually calculated variable, to the SMA image. So we're using the .add bands. Okay, so this palette is the one that I showed you as the first script linked earlier. So it's a very long list. We don't need to include that in this direct script. You can just reference it here with a require. So the new variable for the palette will be called NDFI colors. We'll select 3 bands to visualize, and we'll add that color composite to the map. So this will be a Landsat 5 RGB, and then we'll also add many more. So adding the soil itself, the GV, NPV, shade, all of them, basically. Oh, and the normalized GV and NDFI. Okay, so we're a bit further down in the chapter now, if you're following along in the book. So we'll use the get water mask function. So we'll apply a water mask a little bit later down. You can use the variable below to get the cloud mask too. So there is a band for cloud. So SMA.select cloud greater than or equal to 0.1. And then the get water mask for SMA function is applied to get the water variable. Okay, finishing up here with the first checkpoint. The variable cloud water mask is created and applied. So the final masked NDFI is the SMA image.select the NDFI band, updating the mask to the cloud water mask. So no water areas or clouds should be present anymore. And you add that final layer to the map using the NDFI colors palette. So I'll refresh. My auth token has expired. Okay. Okay, so going back to checkpoint 1, or A3.4 checkpoint. Let's run that. And you can see many, many different images are now printed to your map. If I zoom out a bit, you can see this is the whole Landsat image. And if we want to, I'll zoom into a certain area over here that looks like it's more agriculture. And then there's likely some forest here as well. So if you're looking at just NDFI, that would be densest in the forest in the highest values versus its lower. Looks like yellow values and pink where it's no vegetation. Okay, so feel free to explore all of those images more, but let's go to the next checkpoint, A3.4B. So if you're following along in the book, we should be right about here. So this is change detection. So comparing the NDFI for 2 points in time, not what happens in between, but just start and end, comparing those two. Okay. So I'll skip past all of the script that was in checkpoint 1, and let's go through what's in checkpoint 2. So now you're selecting 2 Landsat 5 scenes on which to apply the SMA model. So image at time 0 with selected bands, that's from Landsat 5. Run the SMA model using get SMA fractions, that function we had from above, inputting the image and our defined end members for soil, GV, etc. We'll center the image on that part of the map now. And these are just visualization parameters that we'll reference later. We'll add this new image from a different time period to the map. So this is going to be RGB, and then we'll add it for soil, GV, NPV. The function get NDFI calculates the shade in GV, or normalized GV, from the SMA bands. So we're repeating what we did before. and adding that to the map. Here's the second Landsat 5 scene. Okay, at line 245, then we combine the two NDFI images into a single variable. So it gets a bit more interesting when you do NDFI times 0 dot select the NDFI band, and then you add the NDFI band from time 1. So it's in one image now, and rename those two bands to NDFI T0 and T1. So now we can directly calculate the NDFI change. So we're selecting from the image we just made, NDFI time 1 minus NDFI T0, where we started, and renaming that our change band. Okay, now we want to make a histogram of the NDFI change image to define the threshold values for classification, making the histogram and setting the options up here. So UI.chart.image.histogram is a user interface for making the histogram, selecting our band of interest in our AOI, and we're going to set the series of the NDFI change. And all these options were just defined here for how it's visualized: font size, title, how do you make it pretty, and print that histogram to the console on the right. Okay, I'm gonna hit run just so you can see that printed to the console while I keep going. It's still putting all of these on the map. So you could change that to false if you don't want to see them right now. You can expand this by clicking this button on the top right. So this is the NDFI histogram we have created of change. So is there a negative change, a little bit of few pixels of positive change, and mostly around 0, which would be no change. So we need to find a threshold now. Well, firstly, classifying the NDFI difference image based on thresholds. We'll use this a bit later. So the NDFI change expression, it's specifying values where there's no change. So between greater than or equal to a negative 0.095 and 0.095 positive, we'll say that's hardly any change, so we'll consider it no change. And then we've got one we'll call it logging, but also just degradation or a subtle change within these thresholds, versus a large change of deforestation, and a positive change would be vegetation regrowth. So it's classifying it into those thresholds. Use a simple threshold to get forest in the first image date. So just in T1, select NDFI T0, greater than 0.6. We'll consider it forest if it's very high NDFI, and add that layer to the map. May not be perfect, but that's a decent threshold. And then we can apply an NDFI change. Visualize that. That's the difference. Adding the forest from T0 and the changed classification. And this is referencing those: what is no change, what is degradation, deforestation, and vegetation regrowth, with paletted values. So let's look at just that changed classification. Actually, back it up. Here's the NDFI change. Those red values and dark blue values would be of interest. The NDFI difference. A forest T0. I think this is just a binary layer of what is above zero point 0.6 NDFI, and then the change classification between time 0 and time 2. So the histogram is just run in this little area. So let's zoom in to that region. I'll turn off all these other images just to save us time where it's trying to visualize a lot of things. Okay, so the NDFI difference map, those positive values are basically, I think the red is where it has been lost, and then the light blue should be the regrowth versus the lower in between values for degradation, and then there's plenty of no change. Okay, so feel free to explore that more, but that is a difference between 2 points in time. And then we'll move on to the next section, section 3, where we talk about coded, a fancier algorithm for mapping change using a time series. So this is checkpoint C, and this is referencing coded, which is an algorithm written by one of our authors, Eric Bullock. And you can reference the full read the docs via this link, which will talk more about the background of the algorithm. But in brief, these are the general steps of coded. It creates an NDFI time series graph that observes regular NDFI variations that are just seasonal changes, typical of that landscape. And then it flags forest disturbances over time based on NDFI change outside of that normal harmonic range. Then you can classify the land cover types before and after a disturbance. And if it had transferred to a non-forest from a forest, that would be a deforestation, versus if it was just subtle and stayed forest, that would be degradation. Okay, let's go back to our checkpoints. The first one is where you will start. A3.4C, you should make a copy of this and start copy pasting in the pieces one by one on your own. This is important because it's referencing an external script via require. These commented outlines are the official coded repository hosted on Eric Bullock's repository. But we have opted to create local versions of those resources within the Google Earth Engine Books repository to keep things stable, just in case any changes happen down the line within the official repository. This will still work. You are more than welcome to uncomment these and switch it in your analysis. But if you get any errors, you'll have to troubleshoot any of those changes that have since happened. But these ones should work for you. And you can even open up that script and look at what's happening in the backend for that required piece. So I'm going to utilize the checkpoint D to talk you through it, but you'll be copy pasting little by little. So we start with a geometry of an image from the previous section, just that Landsat 5 scene. We'll get a cloud mask image of Landsat imagery. So this is using the utils. So it's referencing this external source to get Landsat scenes from 1984 to 2021. And it's making a forest mask by just referencing Hansen forest mask. And then you can threshold anything greater than 40 tree cover from Hansen's data set and Global Forest Watch will be considered forest. This is also assuming that there have been training samples collected, which these are just forest or non-forest training samples. So we have a pre-prepared data set based on the Hansen map. So just extracting from where this was forest and not forest. Values of 1 are forest and non-forest are 2. And those have been pre-prepared. If you want to make a data set of this yourself, you can reference earlier chapters or go to the coded read the docs on how to make those. These are some variables applied within the coded algorithm. Changing these will alter your results. So you can start with these basic ones and then try changing the different years or the parameters, like the number of minimum observations in a row that are out of the normal to be considered an event, chi-squared probability. These will stay the same, and these will stay the same. Okay, and those are just referenced again in a dictionary. Note, if you are running coded, it's best practice to expand your time period about 6 months to a year before when you're actually interested in the changes happening, so it has a chance to train what normal looks like for that area. So if we run that, it's going to print a couple things to the console. It will print a quick view of the samples, and it will also print a 3-part results file. So not a file, but the results of the coded algorithm. There's the change parameters, the general parameters, and the change parameters you define. General parameters are also defined partially by you and partially in the general script. And then the layers that are created. You can see it's actually finding the dates of deforestation, degradation of when the event happened for multiple events, the magnitude of those events, and then it's classifying a map of the stratification, which would be forest, non-forest, degradation, and deforestation, just for simple classes. Okay, so you'll notice nothing is visualized to the map. It is a computationally heavy algorithm, so visualizing on the fly really doesn't work unless you have a very small area of interest or a very small time period of interest. So I'll skip ahead past that checkpoint. So our last checkpoint has formatting the results for exportation. So taking those 3 results and exporting it as an asset. So you're defining variables like the mask, the change, setting it to int 32, magnitude, and then the make strata. So this is normally what is of the most interest. So the strata applies the mask, the magnitude, the degradation, and deforestation are separate classes. So strata, where deg is 3 and deforestation is 4. And then 0 and or 1 and 2 are going to be non-forest and stable forest. Clipping it to the study area. And there is a magnitude threshold in post-processing as well, which you can read about more in the change the doc or read the docs. And then you'll export your image to asset within just your study area. That can take a good amount of time. So what we've done is we've not visualized that map, but we're visualizing a pre-exported image of the strata. So if you want to export your own, just the strata map is exported. You can run that, shortening the time period, or the AOI. Again, we'll get that to happen faster. But let's visualize one we've already pre-made for you. This is their final result, where green is stable forest, black is non-forest, yellow is degradation, and red is deforestation. So this isn't a perfect way to look at this because we don't know what time period the image base map is below it, but you can see areas that are more subtle, small scale changes showing up in yellow, and then areas that are constantly agriculture and clearly not forest are black. And these really stable areas that are away from human intervention are pure green for stable forest for that whole time period. So let's just look at our conclusions. We've learned about the spectral unmixing algorithm, SMA, and normalized difference fraction index. Both are utilized in the coded algorithm to get a good map of what degradation is. NDFI is sensitive to subtle changes, which is why we utilize it so much for mapping degradation. And it's just the chosen index for that purpose, typically. We represented two examples of change detection, both the straightforward two image differencing and the NDFI time series approach, specifically the coded algorithm. To explore more, I recommend adjusting those parameters within the coded algorithm, like the chi-squared or the number of consecutive observations, or the post parameter of your magnitude threshold, or the time period of interest, and see how your results change. Apply that in your own area. And once you finish and export your own results, then you can change the asset path with visualization and visualize your own map of what degradation and deforestation might look like. So that's the end of the forest loss and forest degradation change chapter. I hope you learned something interesting.